Yes, dear colleagues, I'm happy to start our today's seminar. Our speaker is Professor Euich Miztani, and he will tell us about uh, time-independent special theory of relativity. Let's welcome.
Thank you for introducing me, Professor, and I appreciate giving me this opportunity to make a presentation today. All right. Let me start my presentation right now. The title is Time-Dependent Special Theory of Relativity. Abstract. In the process of about Einstein's establishing the theory of special relativity, the principle of relativity is completely based on geometrical description. On the other hand, the electro-magnetic theory is purely algebraic and complicated. Minkowski's work extended it for the four-dimensional space-time, which is purely algebraic as well. However, we are able to understand Einstein's idea much simpler and more phenomenally in chapter 1. Such a description of special relativity will facilitate researchers in spintronics to consider the relativity.
Okay. Can you please speak more clearly?
Oh, sorry. Sorry. We are able to understand Einstein's idea much simpler, more phenomenally in chapter 1. Explain it. Such a description of special relativity will facilitate researchers in spintronics to consider the relativistic effect. Besides, it leads to an unknown special orthogonal group in real space, known the indefinite orthogonal group S113 in chapter 2. Furthermore, long-standing concept.
We don't see your slide.
Okay. Oh, really?
Yes.
What happened? Just a second, please. Oops. 2. Okay. Is it all right? Can you see the screen?
No, nothing is visible. Nothing is visible.
Really? Just a second, please. What happened?
I don't know.
What should I do? I do the screen again.
It was here, but now it isn't.
Really? What happened? All right. I broadcast again. So can you see my screen?
Yes.
Oh, all right. Thank you. Anyway, I indicate an unknown special orthogonal group in real space. And furthermore, long-standing controversies of displacement current will be shown in chapter 3. In this talk, we discuss the complete geometric special relativity and its now regrouped in real space. Besides, I will show new Lorentz covariance. I got a covariance when Professor Holger Beck Nielsen, who is a professor of Niels Bohr Institute, gave me a hint. I could derive it. All right. Chapter 1. Net observation of special relativity, different from Einstein. First of all, what I think of observer when when in the static system, kappa, as shown in figure 1. So, sorry, just a second, please. Why it doesn't work? Okay, video one. And inertial system kappa dash in figure 2, you know. A ray of light to the observer, ray of light, decline to the x dash axis by the aberration based on the principle of the consistency of the right speed. Means right there, you know. As the velocity of the observer approaches.
Yeah, excuse me. And where is the observer? Is he on the left?
Sorry, could you tell me again, please?
Where is the observer? Is he on the left?
Oh, yes, observer is, just a second. Observer in the static system is here. Oops. Here, you know, and observer in the inertial system here are moving V like this. And we assume only ray of light, always perpendicular to the observer. Sorry, what happened? You know, like this, you know. So like this. Only perpendicular means to the observer in the static system. Naturally, it is real like this, you know. So we do not assume ray of light, you know, coming to like this in the static system. In this case, we need a Lorentz transformation. If thinking like those rays, you know, showing right group right like this, you know. So we do not assume those rate of light. All right. So formula of relativistic aberration cosine phi dash equals, you know, like this, you know, equation 1.1. Well, as I tell you, we think only the case of equation 1.21 and 1.3. You know, it corresponds to one figure to show, you know, right there. Like this, yeah, like this. Discussing special relativity from a geometric viewpoint, relativistic aberration plays a key role. By using only those two equations expressed in figure 2, you know, we read out Lorentz transformation. You know, that is a key. So that is why the title of my presentation is Time-Independent Special Theory of Relativity. Relativistic Coulomb force. We know that the Coulomb force between an electron and the position moving with relativistic speed is considerably reduced. It will be explained by the operation we discussed about. You know, so in the case of Einstein, he derived the results through complicated algebraic calculation. However, we don't necessarily do it. I explain it now. Coulomb health between an electron and a positron moving with the relativistic speed is considerably reduced. It will be explained by the aberration we discussed above, as shown in figure 3. When a pair of electron and positron travel horizontally, a relativistic still, and observer detect the observer. Detect the electronic field E vertical by the relativistic aberration. So observer is in the static system. So the observers, the electric field observer sees is E vertical, right? So E vertical. So the length is we will be able to like this, so I explain, since only a vertical component of the electric field is active for the electron, relativistic Coulomb force F dash from the observer's viewpoint. That is F dash equal Q E vertical of shown in the figure 1.4, where Q is quantity of electric charge. E vertical is vertical component of E, as shown in figure 3, by the static system. And since E vertical equals E sine theta from figure 2, equation 1.4 is F dash Q E sine theta, and theta is here. From EQ 1.3 and equation 1.5 is F dash equal QE square root 1 minus cosine theta square equals QE square 1 minus V over C square. We know this factor. We know the factor very well. That corresponds to the general expression by Einstein. All right, of course, that is not only the case. So we think of relativistic electromagnetic field. Relativistic magnetic flux density Vx dash, Vy dash, and Vz dash expressed by, of course, means relativistic Maxwell equation. So Vx dash equal Vx, Vy dash equal beta means, square root 1 minus over V over C squared, the I underline beta means. So those equations are derived from Einstein. So please refer to those equations, very popular equations. I paste the link to the translation into English. Means his paper of Einstein in published in 1905. So a second. I paste the link to the Zoom chat, so you are able to see the presentation slides. Just a second. Hi, Elia. Thank you. All right, there you go. Please check it out. So I get back to the slide. So just a second, please. All right. So let's just think those equations, and I show how to explain those equations by geometric method. So first of all, let us think of the magnetic flux. Those three equations. In the original paper by Albert Einstein, those equations of 1.7 to 112 means, are derived from very complicated algebraic expansion. However, contrarily, let us derive them by simple geometry. As shown in figure 4, an observer moves at a speed v around the positive y-axis and detect the decline magnetic flux dz of the statistic system. So observer is he. Oops, sorry. He, observer. And observer is moving at speed of v, expressing the magnetic flux by the coordinates of the inertial system, b equals b dash y sine theta plus b zeta dash cosine theta. So, means this vector and this vector, and theta is here, So cosine, bz theta and by sine theta. Bz cosine theta, and by bz cosine theta. So see. By cosine theta. By sine theta. By sine theta. By sine theta.
No.
Something's wrong. BZ.
Hello?
Hello, yes, hello.
Oh, is there some problem? Sorry.
Yeah, let me think. Probably okay.
Okay.
BZ sine theta. BZ sine theta. Yes. BZ sine theta. Equals B1 sine theta. B1 sine theta. B1 sine theta. Maybe I give theta to a wrong position, but it will be okay. Anyway, I go on BZ equal so BZ is here, this is sorry, yes, magnetic. Sorry, just a second, please. ちょっと今話しちゃうので待って。Sorry, BZ is RAM, but this is originally magnetic field in the static system, but RAM like there because observer moves. So since sine theta is like this, cosine theta is like this. Figure 2 and figure 1.3 and 1.30 is expanded like this. And since beta is like that, so we expanded 1.48 like this, B denotes a vector of the decline magnetic flux density of the static system. It means BZ is so I sorry BC just a second. BZ BZ denotes a vector of decline magnetic density of the static system. B dash G is vertical component, and BY is horizontal by the inertial system. So this it means here this is a point. This is a point. Sorry, this is a point. This is a point. So because since BY dash is horizontal to the direction of the observer moving at the speed of v, so by equal by dash by the consistency of the speed of light claimed by Einstein. So the equation 1.13 is one like this. So the point is here. Sorry.
No, it's unacceptable. Turn off your phone.
Sorry. Yes, I'm sorry. I turned off the switch. Sorry. I turn off the phone. Just a second. All right. Sorry. I turn off the phone. So by the way, since B dash Y or BY is perpendicular to bz dash. It seems to the observer as if it is an electric field. Considering by dash or by as an electric field, then substituting Maxwell's equation B equal E over C to correct the magnitude gap between B and E. So equation 1.15 is, 1.16. Sorry, what happened? So the key is here. So,
well, maybe you can show us your goals. Maybe you can show us some final formulas, what you are going to obtain.
Here, 1.17.
So is it your so is it your main result?
Right, yes. Main result, but of course, correspond to the equation derived by Einstein.
Excuse me, but what about general relativity? Are you talking about special relativity?
Yes, special relativity.
Okay.
Because we are talking about relativistic Maxwell equation. So it is a topic about special relativity. So it corresponds to the original equation 1.9 by Einstein. And we do the same. Let us think of B dash Y in the same way. Remark, we discuss them in the right-hand system. Oh, sorry, left-hand system. Means this system. So this system is very tricky. So we do the same thing, like this, like this, like this, like this, like this, like this. However, it does not correspond to the original equation 1.8. See 1.8, just a second, get back to the equation. 1.8 is, I'm sorry, plus, plus. So doesn't correspond. So we have to take, that is why we have to take the left-hand rule. So by using left-hand rule, we, change according to the left-hand rule. If so, the graph is explained like this. F dash Y. So assume Lorentz force. B dash Y positive and negative is Z. So think of the graph, change based on the left-hand rule. EZ become negative. So expanding equation 1.23 is like this. So it corresponds to equation 1.8 by Einstein. This one. So calculation is very, very simple, far simpler than Einstein's. And we do the same, process to other equations, like this. Oh, this is, the case of figure 4. So because we do the thing like this, so have to think the graph based on the right-hand rule. So in that case, b dash y is negative, bz negative, b dash z is negative, So we do the thing to check like this. No, sorry. Like this, We have to, think of the right-hand rule. So of course they all negative, the results is the same, negative, 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 no, positive, negative, positive. So like this. Oh, so. Yes. Oh, sorry. Sorry. I was confused. Sorry. Negative, negative, negative. So the equation is negative, negative, negative. So it is the same, one this case, 1.15 here. And do the same for the electric fields. So easy equations, those things are like this. And finally, the original equation 1.7 about EX and BX. So this one, this one, on this one, we just think about it like this. The original equations of 1.7, 1.10, magnetic field and electric flux are easily verified by the constancy of the speed of light as shown in figure 11. Like this. So bx equal b dash x, ex equal e dash x. By the way, what happens and what does it mean from our viewpoint? If v equals c, then sine theta equals 0, and cosine theta 1. The result is like this, like this. It phenomenally suggests that the magnetic flux totally declines by the relativistic aberration as shown in figure 12. It then totally corresponds to Maxwell's equations. Means Maxwell equations, And chapter 2, the derivation of a new Lorentz group SO3 in real space. From our discussion, it is apparent that the rotations of electric field and magnetic field in the inertial system, because ray of light decline, the observer accelerate, and the close to the right speed, like this. This is rotation, as it is as if a rotation. So it naturally seems to be SO3R in the Euclidean space. Now in the indefinite orthogonal group SO13 in the Minkowski space. This SO13 is well-known Lorentz group. In this case, T is fixed. So 3 means, XYZ is rotated. So that is, called pseudo orthogonal group. Pseudo, So let us derive the group in the same way as we have discussed in chapter 1. So, that's what I mean, the ray of light declines like this, like this, Based on figure 14, we can denote as follows. Sine phi equals cosine theta. It means here, phi and theta. So cosine phi equals sine theta is like this. So we mainly use phi for descriptive purpose. So it's convenient rather than using theta. First of all, let us think of a specific case as figure 12. Figure 12. Oh, this one, on the right hand, graph on the right hand. Let us think of a specific case as, multiplying both sides of equation 1.9 by this factor. Sorry, what happened? Sorry. This factor. Then the equation is like this. When V equals C, right hand side is here. Right hand side equal cosine theta. In the case of pi over 2 equals 0, and right hand side is like this, here. Equation 1.17. Probably this one. No, sorry. Yeah, here. Yeah. EY equal BZ, and equation 1.18 is EZ equal minus BY. Those are Maxwell equations. When V equals C in the same manner, from the results, like this, they are equivalent to like this. Then they are naturally related to SO2R, if thinking like that. Based on the facts above, let us discuss equation 1.72 on 1.12 in the same way. Firstly, let us think of the magnetic flux density, solving equation 1.9 for BZ. the expansion is denoted by equation 2.1. Sorry. Oh, yes, this one, yes. This one. So since E over C equal B dash by the consistency of the speed of light, BZ equals 1 over beta, BZ dash plus V over C squared, EY equal BZ dash cosine phi plus B dash Y sine phi. Likewise, solving equation 1.8, equation 1.8, equation 1.88. I'm sorry. Equation 1.8. Yeah, this one, it's this one. The expression is right there. Just expressed by sine theta and cosine cosine phi and sine phi. Since E over C equal V dash by the consistency of the speed of light, the equation is like this. And denoting equation 2.3 and 2.4 by 2 by 2 matrix, sorry. BZ, BY, and like this, like this. The trick is here, BZ on the left hand side is BZ, BY. Sorry. Oh, that is all right. On the what I like to do is make the Cram vector, Cram matrix like BYBZ. So we think the trick, the matrix. So multiplying both sides of equation 2.5 by in this matrix. Right hand side is like this, as a left hand side, sorry. Right hand side is like that, therefore, like this. Then multiplying both sides of equation 2.6 by this matrix. It's like that. So it is, so to speak, SO2R. It's natural because we discussed the relativistic aberration. Only rays of light perpendicular to observer, moving to speed, like this, or observer, like this, So those ray of light looks like, this. for observer in the inertial system. So those rays arise as if rotating, So it's natural, Think right those rotational matrix. So we also discuss the same thing, to electric fields. Those calculations are, here, equation 2.8 to 2.11, So the rotation matrices of equation 2.7 and 2.11 can naturally make a special orthogonal group SO2L. We could consider it as a new Lorentz group. And furthermore, including the equation 1.7 and 1.10, the matrices of 2.7 and 2.11 here, sorry. This one and this one, So we are also able to, that's, like this, So the results are, like this, by dash is bx, e dash y equal ex. So we, merge the component element of x like this. And the application for spintronics, we made the special relativity much simpler, as we discussed. So, it also means we don't need to use tensor, metric tensors like that. So no, complicated indices, for example, invariant metrics or covariant metrics like that, So that will be simpler and convenient, especially for the engineers. So especially, I think application for spintronics will be expected. So the spin of the electron of magnetic body in the static and inertial system, as shown in figure 15, the spin in the magnetic field remains as it appears. The angle between the spin axis of magnetic body's axis and the horizon is naturally denoted by sine phi equal cosine theta equal V over C, as we have discussed. Chapter 3, discussion on Ampere-Maxwell equation in the inertial system. Derivation of displacement current from relativistic Euich. Magnetic Euich. From a viewpoint, as shown in figure 16 on this one. Magnetic field in the static system couple is around the observer on the x-axis, here, And however, as shown figure 17, it will converge onto the line in the x-axis, drawing the Euich means like this, Figure 18 shows when the observer travels at nearly the speed of light. Figure 19 shows at the speed of light, like this, So imagine, for example, you hold a spring, and take on both sides and pull it widely. So, the spring, the coil, the circle diameter or radius, shrink, because when you pull up the spring, it spread line, So imagine like that. So you pull up the spring, it, becomes line. Spring is line. It's when the observer reach for the speed of light. So let us think of the magnetic flux H around the observer in the inertial system. Kappa dash, as shown figure 17 to 19, means those graphs. The original magnetic flux H in the y prime converges onto the x-axis. The observer's speed is close to the speed of light. Since the magnetic flux in kappa dash consists of two components of vector delta hy in the y plane and parallel to the x-axis as shown in figure 20 and 21, means this figure. So I express here, on the vector squares to make it easy to understand. The original magnetic flux H in the y prime converges onto the x-axis. The observer speed is close to the speed of light. So the vector is, like this. The vector is like this. The vector is, sorry, like this. The vector is like this. So considering the declining, so the declines of vectors, curl hx equals like this. And since we obviously curl hx dash is vertical to the factor, it could be considered as an electric flux density d dash. It is a same source as we discussed in the last chapter. B changes to E changes to B from the observer in the inertial system. Such a way of thought is the same as Einstein's. So it could be considered as the yes, in the manner of our discussion in the former chapters. Then from H equals CD, you have to derive the equation, from those equations, and try to calculate and check it out. So equation is changed like this. Especially here. since d dash is equivalent to d by the consistency of the speed of light, we don't need d dash, identify d dash to d. Therefore, the relativistic ampere Maxwell law is like this, where J is electric density. So likewise, we are able to say right there. So as we have seen the results with figure 17 and 18, 17, 17, 17 and 18. Oh, sorry, 18, The displacement current cannot generate a magnetic field because, displacement current, is originally magnetic field, from the observer in the inertial system, a magnetic field looks like electric field. It means, displacement currency. But among physicists, this is controversial issues among physicists. Some say, displacement current generate magnetic field again, but others displacement current doesn't generate magnetic field, but the problem, the issue is controversial, even now. But now we, can say displacement current does not generate magnetic field because, from the observer, magnetic field looks as displacement current, So from this point of view, since the observer moves, the phenomenon also suggests an electromagnetic induction. It means just I will explain it in the next chapter. Yes. So let me go on. Furthermore, since the propagation rate of the electromagnetic wave is always c, the equation of Euich means magnetic fields from the observer in the inertial system. We obtain those equations. And remember, we discussed time-independent special relativity. However, when we discuss the relativistic ampere Maxwell equation, as a result, we obtain, time-dependent, member of the equation. So I participate in organize of the workshop in Brad of Slovenia. Normal request me. I have to solve the problem. So time in this sense, in this issue, it is obviously time dependent. So she requests me, I have to explain in the space, including t, means for dimensional space time. So the discussion of the next subsection is about the issue. So just a second, let me go on. So now we should decide the value of angular velocity omega in the equations 3.6 and 3.7 chiefly. Though it might be omega equals c over r by the formula of angular speed, it could be greater than the speed of light in the radius is microscopic. For example, 0.002, So, in such a case, it contradicts the principle of the constancy of the speed of light. Therefore, omega equals c in the static system. The replacement of W equals c over r with omega equals c will be also, so to speak, in a way, renormalization. Therefore, equation 3.6, 3.6 here, should be described as, like this. And from another viewpoint, to simplify our discussion, let us pay attention to the electrons traveling in the relativistic, in the electric field and the magnetic field, which the electrons generate, as shown in figure 22. 22 here, here. An observer is always in the static system, kappa, and observes the magnetic helix. Remark: these directions of the electric current and the electrons in the electric field are opposite, to each other. Paying attention to the remark, since the observer is always in kappa and the four helix and electrons move at the speed of v, the relativistic Ampere-Maxwell equation for the observer in kappa is like this. So we just discussed a similar thing, but the result of the equation is the same, So please check it out carefully later through the slides, through the link below. I attached at the chat room of the Zoom. Since fact 2, the fact 2 is vertical to this fact 2, it could be considered as D in the manner of our discussions in the formal chapters. Then from H equals CD. So same in our discussion, So relativistic Ampere-Maxwell law is, like this. This derivation will be more faithful to the Ampere-Maxwell equation. The hierarchical equations from the viewpoint of the observer in the static system are like this. So this equation a bit different in the manner of positive, and the negative means here, but it's the same. So what I was going to do, no, sorry, but anyway, basically, the direction, equation is the same. Yeah, but we have to, think several settings and confirm they are correct or not. If they are correct or not. So I'm, discussing, Q3 like that. So chapter 4, the Lorentz covariance in Minkowski space. Our discussion in chapter 3 eventually yield the time-dependent, like I told you earlier, results from the time-dependent discussion. From time-independent discussion. The relativistic hierarchical equations are explicitly means positive, time dependent. And explicitly, obviously time dependent. To scrutinize the results, let us think of the Minkowski metric and check to see if it is Lorentz covariant. So again, the relativistic hierarchical equations from the viewpoint of the observer in the static system, kappa are, those equations. So based on those equations, let us think of the Lorentz covariance. When we call the equations 1.13 to 15 are, like this, They use Lorentz hierarchical equations. Sorry, relativistic hierarchical equations. RHE is short for relativistic hierarchical equations, describing a circle of magnetic hierarchies in the static system. See also figure 24. Figure 24. This is the case. Velocity of the observer equals 0. To simplify, let R equal unit circle, then equation 4.1 to 4.3 are x equals 0, So like this. We can therefore decide a metric SP in the static system as shown in figure 24, metrics, in the static system. Likewise, we can decide the metric SP dash in the inertial system as shown in figure 24. Here, Since the DSP is an infinitesimal arc, DSP equals CDT, means, 1, 0, and 0. So we have to, say right there, From equation 4.7, the Minkowski metric MS in the static system is ms squared equals c squared dt squared plus c squared dt squared equals 0. From equation 1.13 to 15, see also figure 25 here, you know. So the key is the calculation of RW, you know, R dash W, you know. The SP dash in the inertial system is, you know, like this calculation, you know, pay attention to, you know, the part. And calculating from equation 4.9, you know, here, ms dash square equals minus c square dt dash square plus v square dt dash square plus c square open parentheses 1 minus c sorry over v over c square here, yeah, dt dash square. So expanding, you know, the calculation on the right hand side, so equals 0. So from equations 4.8 and 4.10, you know, we can get the results. Therefore, there's relativistic Euich equations are Lorentz covariant. So I think this is important. Remark: any spin in the real space disputes a relativistic sphere, as we have discussed. However, another spin in the internal space is not influenced at all by the relativistic sphere. For example, we know the fact that the non-relativistic Pauli equation is for spin half, you know, particles, as well as the relativistic Dirac wave equation, also for half ones. The spin in the inertial space is always the same. In other words, it strongly suggests that the internal space is not a subspace of our space. That's important because Karuza-Klein theory is based on higher dimensional space is a subspace of our space. How about deep brane in the string theory? Deep brane is a kind of membrane in high, you know, membrane. In other words, a subspace in higher dimensional space. For example, D2 brane is a subspace of our three-dimensional space, you know. Such a way of thought is strange because the nature, you know, suggests the internal space. In other words, complex space, you know, is not a subspace of our real space. So, you know, in this sense, you know, way of thinking of dimensionality in string theory is again what the nature suggests. So conclusions, as we have discussed, electric and magnetic fields orientated perpendicular to an electron traveling at relativistic speed will be ruined by the ruined, by the decline by the relativistic aberration that's shown figure 15. Figure 15. Wait. Yeah, like this, Also, figure 4 is fine. 14 is fine. Similarly, the spin angle of an electron or magnetic body will be affected. In spintronics, in the inertial system, the rotation group in the Euclidean space SO3R will be useful, as you know. Additionally, the long-standing controversies of the displacement current originally studied from Maxwell's hypothesis are solved, like we discussed. It is also Lorentz covariant. Means Lorentz covariant is also discovered. Thank you for listening. This is acknowledgements and references. Do you have any questions?
Sorry.
Yes, please.
Actually, in the chat, there is a question.
Oh, really? Oh, yes. I check the question. Just a second. Zoom. Course action. Well, in Japanese mathematicians can verify principle of Galileo. Principle of relativity has two types: Galileo's and Einstein's. So, he says some mathematicians is able to verify Galileo's type of principle of relativity. I don't know, because I have never imagined like that. So please try to calculation. Please inform me the results. Thank you for your question. Oh, yes. Galileo principle, can be demonstrated. So I'm not sure, because I have never imagined like that. But maybe possible, maybe not. It is all right. Yes, please. I just a second. I text my email address on the chat room. So please email me. My email address is euich@gmail.com. I'm looking forward to your reply. Thank you.
Yeah, thank you very much.
Thank you very much.
Are there any more questions or comments? Okay, if not, let's thanks to the speaker again. Thank you very much.
Thank you very much. Thank you, Sejong Sensei.